Okay. What time is it? We have a few more seconds. Alright, so my friends, Assalamualaikum warahmatullahi wabarakatuh, and a very good evening. First thing first, we'll just wait for your friends to come in. Okay, just a friendly reminder that you guys still need to sign in your attendance, okay? Because last week and the week before that, I only have like 6 participants. Okay, so make sure you go to Spectrum, open the link, sign in for your attendance for today. Okay, but prior to that, the numbers keep on reducing. It doesn't really matter, but it's best for you to keep a record, because towards the end of the day, if something is wrong, I mean, for whatever reason, your I don't want to say it, but so in case in the future you want to revisit, you want the university to relook at your final exam marks, for example, what they will do is not just look at your marks, but also looking at your attendance. Okay, so if your attendance is not as per the university requirement, then I'm not sure whether they will process your whatever request that you want or not. Okay, so just to be safe, just make sure you key in your attendance, so that whatever happens in the future, in case you want to do something, there is a record that you actually attended the lecture. Because again, even though the lectures are all recorded, towards the end of the day, I do not record whether you have watched the videos or not. I can do it, but I don't need to do it, because towards the end of the day, what matters is the live lecture. All right, so last week what we have looked at a little bit on solid phase peptide synthesis. We've stopped in this particular page. Okay, so we're gonna continue a little bit, finish up on the lecture materials on this lecture 4, and then we move to lecture number 5 if time permits, which definitely I think we will. All right, so we've looked at SPPS, we've looked at SPS last time, solution phase synthesis. So what is the main difference between those two? So SPPS is basically, describes solid phase peptide synthesis, whereby the synthesis of peptide is being done on a solid support. Okay, again, it doesn't mean that one is solution, one is a solid. It doesn't mean that the solution is being done in the solution while the solid is being done on the solid. It is being done on the solid, but nonetheless, solution or liquid or solvent are still needed. Okay, so it is not 100% solvent free. Okay, so the naming system solid comes because the peptide is grown or synthesized on a solid support. So imagine that one is a solid support. What will happen is you will grow your peptide on the solid. Okay, so this is why we call it as SPPS and not simply just SPS. Okay, and again, I think I mentioned about this last time. The approach is C to N synthesis, where you start off with the C link or C. If you have a sequence of peptide, you start off synthesizing with the C amino acid first, followed by the N. Okay, so you move from the C sequence to the N. So if you have a GGGA, therefore the first amino acid, if you are to do a solid phase peptide synthesis, is you will start off with A, and then you move to next one, and then the next one. Okay, so the first generation of solid support is being shown as here. Okay, so this is what we call as the Fit Resin. So what Merrifield did was, instead of synthesizing a polymer, so he functionalized part of the polymer and making it during the synthesis, making the polymer materials into a kind of like a spherical shape. So it's different than, even though it says there polystyrene, so it's not the same as the polystyrene that you use for food, and it's, well, the material, the building block is the same, okay, but the shape, the structure itself is totally different. Okay, so this is an example. If you have GKAG sequence, again, if you have when you write a sequence, you start off with having an amine on the most left-hand side, okay, and your carboxyl is on the right-hand side. So this is how we write sequence. Does it matter? Well, yes, because internationally everybody is using the same way of writing. It's the same way as if you write, the word peptide. You write it from the left to the right. You don't write it from the right to the left. Well, you can, but some people might get confused on the way you write, or they might not understand what you're trying to convey. Okay, so this is kind of like a standard nomenclature on how you write the sequence of peptides. So always amine on the left-hand side and carboxyl on the right-hand side. But what if you want to change it around? So if you still write it as GKAG, but what you did was actually switch everything around, what will happen is so if, say, you write it like this, okay, the first one, what you will see is you'll see an amine over here. Okay, so you have your first glycine, and then you will have your amine. Okay, so this is how the structure will look like from the left. But if you swap it around, where you have a carboxyl on the left and an amine on the right, what you will get then is a slightly different structure. Okay, so does it matter? Yes, because we've looked at secondary structures, and we've looked at how the amide bond sometimes, in some cases, well, in terms of alpha helix and beta sheet, we do know that they are very critical to form a hydrogen bonding between two parallel sheets, for example, for beta sheet, or between 3.6 amino acids per turn for alpha helix. So it is very important. So you cannot simply just switch it around. If you do, well, basically, instead of writing it like this, what you should be writing it is like that. Okay, so it's slightly different in terms of structure. And of course, synthetically, if you choose number 2, then everything will be, haywire. Okay, so basically, this is just to show you, you have your resin, polystyrene, you have a linker in the middle there, and then what you do is you couple first amino acid. Once it's completed, you move to the second one, and then you third one, and then to the fourth one. So this is why we call SPPS and SPS for peptide synthesis as stepwise synthesis, because you are doing it one by one amino acid after another. Okay. So this will be kind of like a bit more detailed example in terms of the steps. So the first one, we will look at this orthogonal chemistries in the next few slides. But say, for example, you want to synthesize BOC, TBU, SPPS having the same sequence and GKA, G on a solid support. So imagine if that one, the square is your basic block for your amino acid, while the circle ones are your protecting groups later on. Okay, so this one is your amino acid, the other one is your protecting group. So how do you actually synthesize this? Well, of course, as I mentioned previously, you have your solid support on the right-hand side, and then what you want to couple first is glycine. So glycine will be number 1. So if we are to react your amino acid and your resin or onto your linker, so what is actually happening? So the first step is for the C-terminal carboxylic acid to be attached to the solid support. Okay, and it is via SN2 reaction, as we've seen previously multiple times. If you see a halogen, and if the halogen is no longer there in your product, then you can expect either it will go SN1 or SN2. Okay, in this case, it is SN2, but what is missing here is base. oops, okay, plus a base. Because to the end of the day, if you just have a carboxylic acid and a chloride like this, it will not simply just react, and this will not happen. Okay, so this one will not happen because to the end of the day, the lone pair itself is not strong enough to react in just simply. If it's an acid chloride, then yes, you can. But this is not an acid chloride. This is simply just halogenated entity. Okay, so you need a base. Why? Because the first step is for the base to deprotonate the protons on the carboxyl. Okay, so deprotonation, where you have now a negative charge, or even though it's a partial charge, while it's distributed, it is still more reactive than simply carboxylic acid in this particular scenario. Okay, so when you have a carboxylate ion like that, so then you can have an attack on that particular carbon, and chloride will go out as a living group. Okay, so this is the first step. This is pretty much the second step. The first step is the deprotonation, and then the second one is the attack. Okay, and then this is the product that you will get. So you get a first conjugation. So now you have successfully conjugated your first amino acid onto your solid support. Okay, and again, we've looked at previously on during the summary of peptide synthesis, you need to remove your protecting group so that you can add the second amino acid. So in this particular scenario, because it is for bulk TBU, orthogonal synthesis, so to remove the protecting group, you use trifluoroacetic acid or TFA. Okay, so there's multiple ways by which you can do it. You can either use neat or 50% TFA in DCM. So these are all widely used synthetic approach. Okay, or you can even use a 10% TFA in DCM. It's still all good. It's just that as the concentration of TFA reduces, then it will definitely increase the time it takes for the protecting group to actually fall off. Okay, so this is basically just a very simple basic reaction. And then you remove your bulk protecting group, and to the end of the day, what you'll have is you have a free amine. Okay, and then the free amine group can now react with the incoming second amino acid. So in this case, an amino acid which has already been activated by DIC, okay, but again, DIC alone, if you look at this structure itself, you can get a reaction. Okay, but it is not as active. So that's why if you have read a little bit on peptide synthesis, DIC are normally combined with HOBT, okay, HOAT, and stuff like that. Okay, the structure is, if I recall correctly, something like that. 1, 2, 3. Oh, I think I missed. Yeah, it's correct. Okay. Right, and this has another kind of like intermediates in the middle before it actually forms the MR bond. Okay, but nonetheless, this is just a basic step. That's why I put there, etc. HOBT or HOAT, HOCT. There's a lot of chemicals that can be substituted here. Okay, and then step number 4, we just mix. So of course you pre-activate it. Okay, so pre-activation here means that you don't mix everything together. So if you have a reaction vessel, this one is the solid support, okay, with the first amino acid already in there. So what you will do is you pre-activate the second amino acid. So amino acid number 2 is there, plus the IC, for example, plus HOBT. Okay, and of course, a little bit of base. Okay, so you pre-activate it, meaning you do it outside of the environment, and then after a while, you're gonna transfer it here. Okay, so that's what it means by pre-activation. So that's why step number 3 and step number 4 are split into 2, okay, because you don't do it in situ. So in situ means you are actually doing everything there, but this one is pretty much you are doing it in 2 separate vessels before you actually mix them together. Okay, so once you have mixed them together, then you get your second amino acid coupled to it, and you repeat the cycle. Okay, you keep on repeating, removing the bulk protecting group again, pre-activate, and then you mix them together again. So you just go and repeat it until at one point you manage to get all the sequence that you want. Okay, in chemistry, protein is synthesized from which one is this? C terminal to N terminal. Okay, put the arrow there. I have no idea why, but as I mentioned, you start from C, you move to N. Okay, and step number 5, once it's finished, blah blah blah, nothing. Okay, so because the synthesis is repeatable, as you can see, it's kind of like a loop reaction, so to say. Okay, so this technique is easily automated. We will look at a few examples of an instrument that is actually being developed for peptide synthesis. Okay, in comparison biology, you start with N2C, as I mentioned, and as we've looked at a little bit, like very tiny bit, into 006. Okay, and finally, on the final step, the X step, what you do for BOC and TBU, base SPPS, you treat the whole thing, okay, the resin and the peptide with protecting group with very, very strong acid, hydrogen fluoride, okay, and hydrogen fluoride, if you do know, it is gas at room temperature. So to do this, you actually need a very, very controlled environment. Everything is being done in a special fume hood that you don't mix with something else, and you use a lot of dry ice to actually try and transfer and condense the hydrogen fluoride, so that it will not be in a gas form, but rather in liquid form when it's reacting with your resin. Okay, and in HF, what you will get is pretty much remove all protecting group, you remove all the BOC, you remove all the TBU protecting group on the side chain, and finally you also remove the peptide from the resin. Okay, so towards the end of the day, you'll get your peptide, and this is what you, well, after that, of course, you can just purify it, and or perhaps if you want to use it, then you can use it for whatever reason straight away. Okay. All right, so that's about it for peptide synthesis. That's the cycle. Pretty much it's straightforward. And what's different is the types of protecting group or combination of protecting group that you can use for SPPS. There are quite a few, not just 2, but these 2 are the main ones, or the ones that are highly commercial and are widely used worldwide. So one is what we call as BOC TBU. So these are orthogonal. Why? Because BOC and TBU are complement one another. So both of them are still acid labile, but TBU is more BOC is more susceptible to weaker acid compared to TBU. Okay, so that's why to remove TBU you use HF, but to remove BOC you can just simply use TFA. But it doesn't mean that if you use TFA, TBU will not fall off. No, you still have a little bit of side reaction normally. So if you use a neat TFA, for example, and perhaps you'll get within 1 minute you'll get 100% BOC deprotected, but TBU probably like 0.1% actually deprotected. Okay, so you still get a majority of your product protected on the side chain. Okay, so this and the second one is what we call as FMOC, BOC orthogonal chemistry. So what are the main difference between those 2? Why do you use BOC from the one orthogonal chemistry and then you use it into the other one? Well, this is because FMOC is not acid labile, so this one is a base labile, while BOC is an acid labile. Okay, in comparison, both of these are acid labile. Okay, so that's why if you use TFA, you'll get this still falling off or deprotected. But if you use FMOC and BOC chemistry, if you do have an FMOC attached on your amino acid, attached on your resin, for example, because FMOC is a base labile, if you use a base, for example, piperidine, that's what we normally use in the lab, piperidine. Okay, so you can remove this while keeping the BOC intact, 100%. Okay, so and towards the end of the day, of course, the linker for both chemistries are different. There are so many types of linkers. Even there's so many types of solid support, not just polystyrene. But I'm just gonna skip on that. We're not gonna cover about it since it's not really very critical. It's enough for you guys to know on how do you actually synthesize peptide in lab. Okay. Right, so again, this is just a general FMOC protocol. You can just read through. It's basically more or less the same as what I've mentioned. What differs between what we have shown you previously is the reagents that you use. For example, instead of using TFA to remove BOC, you use piperidine or methylpiperidine or some other different bases. Towards the end of the day, when you want to cleave it from the peptide from the resin, so for BOC, TBU, orthogonal approach, what you do use is you use HF, but in case for FMOC and BOC, what you use is TFA. Okay, so if you use TFA, well, of course, since FMOC is not acid labile, just before you remove the peptide from the solid support, you still need to remove the FMOC first. Okay, so you need to remove the FMOC, and then finally you use TFA. You can use HF, but HF is more dangerous, so normally people will tend to use TFA to cleave it off the resin. Okay, so what are the advantages of SPPS in comparison to SPS? Well, number one is quick and seamless. You can grow peptide, purify it by simply just washing off the synthesis vessel or column, okay, with an appropriate solvent, for example, DMF or DCM or what's the other one? I can't remember what's the other one on top of my head now. But there are like 3 main solvents that is being used, even though you can just use single one, but there are alternatives, okay? And by just washing it straight away off the column, of course, you can remove the impurities very, very quickly, very, very efficiently. And because the peptide is covalently linked to the resin, it will just stay intact. It will stay in the column, okay? I don't think I have a picture of that, but to kind of like draw you. So imagine if you have a syringe, okay? So the normal syringe that you use, very ugly syringe, but nonetheless, it's a syringe, okay? So what you do is you kind of like just take off the plunger, okay? So that you can have like a very clean syringe. And what you do next is you put in like a filter paper, but it's not a filter paper, okay? So it's what we call as freight. So normally it's a glass freight, okay? So why do we call it a freight? Well, a freight is where you have like a very, very tiny hole, and the structure itself is arranged in a very, very proper manner that you have like a very, very tiny hole. So this glass freight allows for small molecules, like a very, very tiny molecule and solvent to just pass through. However, your solid support, because it's rather large, okay, so it's not even, well, it's about that size, about 1 millimeter, but still large enough compared to a solvent molecule, okay? So what will happen if you put it here, you have your resin over there. So any solvent that you use, if you pour it up there, will be eluted at the bottom of the syringe very, very quickly, okay? And another advantage of SPPS is automation. So you can actually create a computer and then, you know, program the computer so that it follows the steps of the peptide synthesis. And if you are into doing something like this and automation. I'm kind of like promoting my project. I do have an FYP project to actually look into developing an automation for peptide synthesis in the lab. So instead of purchasing an instrument which is very costly, so I'm trying to build up the automation system in my own lab. Okay, so having this automation system, you can actually synthesize kind of like a high throughput synthesis very quickly within a week. In comparison, just to tell you guys in comparison, during my PhD, I synthesized about, well, PhD takes about 3 years. I synthesized about 20 to 25 peptides, all success ones, excluding all the failure ones. Okay, about 20-ish amino acid peptides. But following my PhD, I work in the lab. Within 1 year working in the lab, I've synthesized about 100 different peptides. So having this automatic peptide synthesizer actually helps a lot, especially because the system can always work 24 hours a day. Okay, so this image on the left and on the right are two different systems that we have. Both of them are automatic peptide synthesizer, but the difference is this one has 12 different slots. So each individual, what do you call it, kind of like a container here, is a different, or well, you can make it a different amino acids or a different peptide sequence. Okay, so it's very nice. Of course, the one that I'm building is not like this, and this instrument costs like close to about 500,000 ringgit. Not that expensive, so to say, but if you were to purchase it in Malaysia, then if you directly convert the price from say US to Malaysia, that would be about 500,000. But if you purchase it in Malaysia, you know how the government works. You always need to purchase from a middleman, and the middleman will always mark up the price, and the price for that is close to about 1 million. Okay. On the other hand, the instrument on the right hand side is a bit kind of like downgraded slightly. Okay, why? Because we cannot see it here, but inside here is where you keep on all the synthesis vessel with the resin, and this system can only hold, if I'm not mistaken, just two different vessels. Okay, in comparison, the other one on the left can store, or you can synthesize up to 12 different peptides simultaneously. Okay, and this is where you put all the reagents and whatnot. And if you notice, that is actually my handwriting. Okay, so these are the two instruments that I've used during my not studies, working. Okay, however, there's still limitation. SPPS cannot be compared to how nature works, because we have looked at on how we've looked at the structure of ribosomes. We've talked about ribosomes into 006 in terms of protein synthesis. Ribosomes are very quick. It synthesizes, or it couples thousands of amino acids in 1 second. Okay, so that's why if you recall, if you have learned about biology, then pretty much you kind of like being amazed on how our body actually works, because each time when you move like that, for example, there's thousands of molecules or peptides being synthesized and degraded multiple times. Okay, and of course, there's very minor mistakes in the synthesis. So protein complexes is different. Different protein will require post-synthesis approach to ensure it function. Okay, so this one is just to talk about the function of a protein. Protein are very complex, and different complexity require different, what we call as post-synthesis approach. Say for example, if what we have looked at is pretty much synthesizing a linear peptide, okay, but in nature there are peptides that are not linear but are actually cyclized. Okay, so it's head to tail cyclized. There's no start, there's no end. Of course, there is a start and end, but when the organism actually use the peptide, it is actually a closed ring system. Okay, so that's one way. There is also a peptide out there, and especially proteins that has a lot of disulfide bonds. Okay, we have not looked at on how you actually form a disulfide bond, but again, it's a very simple oxidation reaction. If you do have two cysteine in close proximity, you just bubble it up with oxygen or even air, a normal air bubble like this. Okay, so it will oxidize this cysteine residues and it forms a disulfide bond. Very, very straightforward. However, this system is very controlled in biology or in bacteria or in our cells, for example. Okay, so it's very, very fascinating. So peptide synthesis is done linearly in organic solvent, therefore there's a lack of secondary structure, and higher, there is another disadvantage. Okay, you synthesize it all in organic solvent, so definitely there's no secondary structure. There can be secondary structure, but not as complex as what we've seen in different level structures of proteins. Okay, so and lastly, disulfide bonds, as I mentioned. All right, so these are just to show you guys an example on the complexity of a peptide. So I've shown previously that you can have a cyclic, and second one is you can have a disulfide bond. This is the third type where you can have a cyclic and a disulfide bond in one structure. Okay, so this is part of my work I've done back in Australia. So that's my name over there. And oh, there's only one. And you can also have a more complex structure where you can have two or even, what's the maximum that I've done? I think 4 different disulfide bonds. Okay, and disulfide bonds are not easy to control, so there's a lot of modification. There's a lot of peptide modifications that you need to do if you were to synthesize the peptide in the lab. Okay. All right, so that is all for this note. Let's move on to the second one. Okay, but if you do have any question, be my guest, just stop me anytime. But most likely you will not have any because most of you guys are at home already. So perhaps you are doing something else and not listening to the lecture. Never mind. I don't mind about that. To the end of the day, I fulfill my task, which is to deliver this information to you. And again, at least for this semester, everything is recorded and you can rewatch it anytime. But next semester or week 8 and above, since it is compulsory for you guys to actually attend the lecture, I might not do any recording and I might not do any hybrid. Okay, it's still pending on how the department wants us to do, but the university and the higher up have already mentioned that on week 8 and above, all lectures will be face to face. Now, this slide doesn't want to open. I'll just close that, reopen it. So we'll just cover this note until wherever we can, and then we will continue on after your mid-semester break. Okay. All right. So what we've looked so far is we only have looked at synthesis of peptides. Okay, we've done that. Okay, we've looked at different structural features of proteins. We've looked at the amino acids, a bit of properties of amino acids. Okay, but we have not looked at lipids. We will look at lipids in the next coming weeks. Okay, and that one as well. So what we're going to look at now is sequence analysis of protein. So we have looked at on how you can actually synthesize a protein. But now, if say you are working in an analysis lab, okay, once you have graduated and whatnot, you are working in an analysis lab. So you also need to know how do you actually analyze the sequence of protein. So there are multiple ways by which you can do it. Nowadays, it's rather if the lab that you're working at has expensive instrument, you can skip a lot of what I'm covering here. But in case if you do work in any lab that does this kind of like simple analysis work, so you might not have the most expensive instrument available for you use. So it is still worthwhile to actually learn about on the basics on how do you actually analyze peptide sequence. Okay. All right. So just looking back to what we've learned so far a little bit, we've looked at primary, secondary, tertiary, quaternary structure of a protein. So just recall what are the differences. How can you identify the structures? What are the important feature or properties of each and every structure levels? Okay, so that one is just going back to the future. Okay, so now if you have a protein, if you're working in the lab that does analysis or trying to discover an unknown, what can you do? So how can you identify the primary peptide sequence? Again, if you have a structure of protein, you can easily solve the quaternary structure. So now you have NMR that can help you solve peptide structure. We also have X-ray crystallography to actually help you to solve the structure. And nowadays, a technique is being developed for what we call it, atomic something. I can't remember on top of my head. But yeah, if I recall correct, again in the future, then I will talk to you guys about it again. Okay, so there's more and more techniques is being developed to actually look at the full structure of a protein. So the quaternary structure or the tertiary structure. Okay. However, and of course the secondary structure, there's also a method. You guys perhaps have learned about circular dichroism. Okay, or CD. Circular dichroism is a technique, it's a chemical technique that look at the polarization of light. So remember when you learned about enantiomer, right? RNS or LND. So when you have a mirror image enantiomer, how do people previously identify whether it's a L or D, for example, for amino acid? Is by looking at the ability of that particular molecule to polarize light either on the plus side or a negative side. So either clockwise or anti-clockwise. Okay, so the same concept is being used to identify secondary structure. If you, I'm not going to cover about it in this lecture. It's just an extra info for you guys to know. We can actually use circular dichroism to identify or to look at what is the secondary structure present in your sample. Okay. However, for primary structure, again, as I mentioned, if you do have an expensive instrument, then then you can actually use an instrument that has an MSMS feature, or perhaps MSMS, or triple MS, to actually identify your peptide sequence. Okay, but if you don't have that, if you have a slightly lower version of an MS, for example, just a simple LCMS, okay, so you can still do peptide analysis or protein analysis or protein identification. So how do you do it? Let's have a look. Okay, so imagine that again you have an insulin. So if you recall previously, insulin has two chain, okay, two chain, A chain and a B chain, and then between those chains, there are three different disulfide bonds. Okay, so it's a complex nature, but not so complex that it is a cyclic. Okay, so it's not cyclic, but it has two peptide chain and at the same time three disulfide bonds. So how do you actually, how can you actually analyze what is the sequence of insulin? Now, I divided this into a stepwise process. Okay, so you see numbers here and then in bold. So number one is first you need to definitely reduce or you need to break the disulfide bridge. So that is number one. That is the first step. Regardless of what different proteins that you have, you can always proceed with this particular step. Okay, so how do you reduce it? You just simply react your proteins in normally either aqueous solution or even you can react it in organic. It doesn't matter because at the end of the day, you don't want to preserve the secondary structure. You don't want to preserve the structure of the protein. You rather want to kind of like, unknot the whole structure. Okay, so first one, you react it to mercaptoethanol. What it does is pretty much it reduces the disulfide bridge, okay, forming two cysteines molecule. Okay, and then once you have that, you proceed to the second step. Okay, but just to tell you guys, this is what we have not looked at. Is the okay, right. So the first one is you reduce it, but to make sure that the disulfide bond does not reform, you can either have two approach. One is you increase the number of mercaptoethanol in your solution so that it keeps on always kind of like stops the disulfide bond from forming. Okay, and while you continue on doing your synthesis, but to continue on doing your analysis, not synthesis, your analysis, or alternatively, what you can do once you have broken the disulfide bond, you can react it with hydroacetic acid. Okay, so it will react forming a thiol group, more on acyl thiol group. Okay, so it stops pretty much, it stops the cysteine from forming a disulfide bond itself. Okay, but it doesn't mean that the sulfur cannot be oxidized. It can. So this one, in the presence of oxygen, you can still oxidize the sulfur. Okay, but at least it will not form a disulfide bond again. And therefore, imagine because we are looking at insulin, and insulin has 3 disulfide bonds. Okay, so once you stop it, once you break the disulfide bonds, and then you stop the disulfide bond from forming altogether, now you can separate the two chains individually. Okay, so you can separate them. So once you have separated them, then you can proceed with step number 2. Okay, this is just what, as I mentioned, you want to break that one, and then you can split the chain. Okay, and then you can move to step number 2, is where you take one of the chain first. Okay, and then there's different options that you can do. So number 1, you can analyze the number and kind of amino acid by full hydrolysis, okay, of the amide bond. So you can just either do full hydrolysis, because again, towards the end of the day, it's an amide bond. An amide bond, you can always hydrolyze it using acid hydrolysis or a base hydrolysis. There's 2 options. But the quicker example that people normally use is the acid hydrolysis. So you can just use 6 molar of hydrochloric acid minimum, and 100 degrees, you boil it for 24 hours. Okay, what you'll get is individual amino acid. And then from this individual amino acid, you can always do HPLC to try and identify what the abundance of the amino acid. But then again, from there, you can only know the abundance of the amino acid. You will not know the exact sequence of the amino acid. Okay, so peptide chain will dissolve, denaturize in 6 molar HCl, high temperature and acid environment, promote hydrolysis. As simple as that. Okay, so this is what you do. So once you have hydrolyzed everything, you're gonna inject it in HPLC, because again, HPLC is a cheaper system than mass spectrometry. So if you do have a standards with a known concentration, it's like how you guys did in your analysis lab. Okay, so you do know at this particular area under the curve, for example, this is equal to 0.1 molar, for example. Okay, so from there you can do a direct comparison, and you can get a rough ratio between the amino acids. Okay, at the same time, for example, for this one, you can see that if this one is your sample and that one is your control, your standard, so from there you can know, oh, in my sequence, my protein or peptide has a serine, has a proline, has a glycine, phenylalanine, and arginine. Okay, so you do know the different types of amino acid belonging or that you have in that particular sample. And of course, if you actually control the concentration, you can know, like for example, that area under the curve is relatively like half the amount of proline. So from here, you can expect that you have a ratio of 1 to 2 to 1 to 2 to 2. Okay, so this is a rough estimate. But again, you will not know the sequence, but at least you do know what are the constituents of your peptide or proteins that you have analyzed. Okay, so it will give you a rough info based on the retention type that you have and area under the curve. Okay, so as I mentioned, by no means illustrate the bond, the sequence of the peptides or proteins. Okay, so you need to do an additional step to actually try and identify what is the possible sequence. Okay, and it is a very tedious process to try and identify the chemicals, the individual amino acid, if you were to do it in the lab. So normally nowadays you don't do it in the lab anymore. Well, we do have, you don't do it hands-on. Okay, so you have instrument to actually help you to do this process. Because again, to the end of the day, it's like how you synthesize it. It is a stepwise reaction. Then if you want to analyze it, you can also do a stepwise analysis, which we will look at in the next few slides. Okay. This method is highly used. Therefore, step 3, let's have a look at step 3. And step 3 has two options. One is a full chemical option, or second one, you can use a biochemical option. Okay. If you heard about biochemical, the one keyword that you should have known now is enzyme. Okay, we'll look at this in the next few slides if you do have time. Okay, so step number 3 is what we call as partial hydrolysis. So step 2, we've looked at full hydrolysis, where you just do a full hydrolysis and look at the abundance of the amino acid. But what you do for step number 3 is basically you take another sample of already separated chain A or chain B. You partially break the sequence into smaller fragments. Okay, why does a smaller fragment takes priority? Well, because if you have smaller fragments, at least you can know, say for example, if you have AGHK, okay, if you do a full hydrolysis, then you get a ratio of 1 to 1 to 1 to 1. But if you do a partial hydrolysis, some peptide might be a combination of AGHK. You might also have a combination of G and H and A and K. Okay, so you have these two options by from a partial cleavage of this peptide. Of course, you can have a more complex system where you have AG, H individually and K individually, but nonetheless, by having a partial cleavage, then you can kind of like estimate now that mass of A and G, if you combine it together, then you know, oh, the A and G is next to one another. Okay, and then you know H and K is next to one another. Even though you do not know whether it's KH or HK or AG or GA, but nonetheless, you do know that these two amino acids are next to one another. Okay, and perhaps if you can get that additional info, G and H is also next to one another, then from there, because you know A is next to G, G is next to H, H is next to K, then you can kind of like combine on the puzzles and pretty much identify what is your sequence. Okay, we do not touch about this particular arrangement again in this particular course. We will perhaps touch it in a different course in the third year if you are taking it. So partial hydrolysis, you cleave cleave the peptides or proteins into smaller fragment. Okay, for example, chain A21 amino acid, you might want to break it into 5 or 6 amino acid. Of course, 5 to 6 is just a rough number. How do you know whether you break it into 5 or 6? Well, basically, a trial and error. Okay, so or based on what other people have reported. So, say for example, if you use a dilute hydrochloric acid, you react it with for 24 hours, then you get full hydrolysis. Then you probably want to try and see what happened if you just mix them and then try and cleave and allow the reaction to react only for 1 hour. What happened? So that is what people have done. Okay, and then from there you can kind of like grab all the information and you do know what is happening. Okay, so the resulting fragment are separated and the amino acid composition for each fragment can be determined using electrophoresis and amino acid analyzer. Okay, so amino acid analyzer is basically just analyzes one amino acid at a time. So if you get a separation like this, then amino acid analyzer can pretty much analyze A and K very, very clearly, or perhaps G and H as well. Okay, amino acid analyzer is a broad term that you will see in the next few slides. But additionally, you can do electrophoresis. Why? Because towards the end of the day, if you have this kind of combination, okay, and electrophoresis is using polarity of the molecule to actually separate them together. Then from here, it's kind of like if you're doing a TLC, right? So the more polar, it moves faster if you have a polar solvent or a polar mobile phase. Similarly, over here, electrophoresis, you always use a current. So H and K is a more polar combination. So A and G will probably move a little bit because again, you need to recall that A and G still has its functional groups. Okay, so you can still move. It doesn't mean that when you have A and G in electrophoresis, it doesn't move. It still moves, but it moves in a slower fashion in comparison to if you are compared to H and K. Because H and K, H is histidine, histidine has an extra amine on the side chain, and K is a lysine, also has another polar side chain. Okay, so from there you can separate them, and then from the separation you can either do another treatment, or if you have a library of say running electrophoresis at this particular voltage for this particular time, a combination of A and G will move about 1 centimeter, H and K will move about 10 centimeter. Then from there you can actually know roughly if you are analyzing an unknown sample, you can just kind of like do a standard matching. If it's matched, then you do know that it's that particular sequence. Okay, I'm just going to finish this and then we will end it here. Okay, so the process is repeated multiple times because to the end of the day, you are trying to get as many fragments as you can so that you can kind of like trying to puzzle up all the information that you have, so that towards the end of the day, you will get your original sequence. Okay, you do know, as I mentioned, if A and G is next to one another, and then H and K is next to one another, and G and H are next to one another, then you can pretty much just combine them together. But you can either be A, G, H, K, or you can also have H, K, H, G, A. Okay, are these two different or similar? Well, I've already mentioned the way you write it is to always have the carboxylic acid on the right hand side and amine on the left hand side. So AGHK is not the same as KHGA. Okay, all right, I think that's all for today. We're gonna stop it here, and we will continue on looking at how do you actually do the processes in the next few weeks after Raya. Okay, so that's all from me. We'll see you guys again on Thursday for our last lecture on SID2006. Thank you and have a good day.
Thank you, Doctor.
Welcome.
Thank you, Doctor.
Selamat balik kampung.